Hello, this is MA280, Multivariable Calculus. I'm Professor Wheatley. Today we're going to discuss projectile motion. In particular, we're going to talk about what I refer to as ideal projectile motion. And what does that mean? It means that we're making the big assumption that gravity is the sole force acting on a projectile in the air. And it always points in the negative j direction, so it always points straight down. And we are missing here complicated things like air resistance, which will certainly affect the way a projectile moves through the air, but that really does complicate matters quite a bit, and for our purposes we care about ideal motions. That's what we're going to look at. Okay, so assumptions. We're assuming the following things: that the projectile is launched at time t equals 0. All right, we're assuming that it's launched from the origin into quad 1 of the plane, okay, and that it's launched with initial velocity v0, right? So let me draw a picture of what I'm talking about here. So we're assuming that, so here's quad 1 of the xy plane, y, x, right? And so we're assuming that the projectile is launched with some initial velocity vector v0. And so v0 makes an angle with the x-axis. So if v0 makes an angle alpha with the x-axis, then the following are true. So there's alpha. Well, let's draw our right triangle and see what's going on here. Well, what are the I and j components of v0 here? So the ith component, there you go, and there's the jth component. Well, remember that cosine of alpha is equal to adjacent over hypotenuse, right? So remember that cosine alpha equals, in this case, say we call this x down here, and we call that y. This would be x over v0, length of x. Should be a vector x, I guess, and a vector y. So the length of x over the length of v0. Well, then what is x going to be? So x will then equal what? Cosine alpha times v0 as such, right? So v0's components, the x component of it is the length of v0 times cosine alpha, right? That's the ith component. And well, what is y? Remember that, not sine of y, but sine of alpha is that over that, y over v0. So y is equal to sine alpha v0 as such. So the jth component is length of v0 times sine alpha, right? So there is your ith and jth component. There's v0 cosine alpha. There's v0 sine alpha. And again, I mean, sine and cosine in the first quadrant are both positive, so it doesn't make a difference whether we put them inside absolute value or not, so we'll leave them off. Doesn't make a difference either way. And the initial position, we're assuming it's the origin. We'll call it r0, and it is the 0 vector, right? So we're starting off down here at a vector r0, traveling out v naught with that angle there. Okay, so that's a nice picture. What else can we say about this, though? So let me erase this over here and give us some room to work. I'll leave our picture up for the time being. So we know that force, the old physics equation, force equals mass times acceleration, right? i.e. F equals ma, ma like that, right? And we know that r of t is the position vector of the projectile at time t. So whatever time t this is, r of t is a position vector. Well, acceleration is the second derivative of position, right? So knowing that, that equation then becomes d squared r over dt squared. Again, I've just subbed in acceleration as position's second derivative, right? Okay? Also, remember, one of our big assumption was that the only force acting on the projectile was gravity, right? That's the only force acting there, and it's acting in the minus j direction. So it's in the minus j direction. So what we have here is we know that F equals m times this acceleration vector. We also know that the only force acting on it is going to be in the minus j direction, so that F is equal to negative mgj, which is equal to m d squared r over dt squared. And here I'm using g represent the gravity constant. So g is the gravity constant, and that's approximately 9.8 meters per second squared. Okay? So two different things that F is, it's gravity and it's this m times acceleration, right? So as a consequence, well, if we cancel out the m's here, what do we get? We get d squared r over dt squared equals negative gj as such, right? So we have this equation. Now, going through the process here takes us a little bit off of our beaten path. I'm not going to do it, but Thomas certainly derives this. Other books do it as well. But if you want to, an exercise that's pretty simple, you can solve this second order differential equation to find an equation for the position vector. For position vector r of t. So you can solve this for r in terms of t, right? And also, if you're going to do that, you've got to have a couple initial conditions satisfied here. And those are, let's see, what are they here? So, r of 0, I shouldn't say r of t, r of 0 is equal to r naught is equal to 0. So initial position is going to be 0. That's one condition to satisfy. And also that the derivative of position is equal to initial velocity there. dr naught equals v naught at time t equals 0, right? So these are both time t equals 0, which I guess I should say up here, it should be r of t, shouldn't it? Yeah, so let me change this to, so these are both satisfied, yeah, these are both satisfied at time t equals 0. So the initial position is r naught, which is the 0 vector. The initial velocity is v naught. If you solve this differential equation with these two initial conditions, you'll get an expression for r. It's a good exercise to test your mind out with. But we're not going to do it to save ourselves a little bit of time. Let's see here. So let me erase this. I will erase our picture now. And the conclusion of all of this is that we have a position vector that looks like this. So we have V naught cosine alpha t I plus V naught sine alpha t minus 1/2 gt squared j. And this is the position of a projectile at time t under ideal conditions in the plane, right? So there are the equations you got to know for this stuff. So this is ideal projectile motion. That's the ith component. That's the jth component. This is in the plane. Okay? All right, so let's make some room to work here. Well, immediately from that, we get two equations that are parametric from the x and y component. So the parametric equations are x equals length of V naught cosine alpha t, and y is equal to length of V naught sine alpha t minus 1/2 gt squared. Right? So there's your parametrics. And so x and y give respectively the horizontal distance and the vertical distance. So x gives what we call the range, which is horizontal distance, and y gives the height. Okay? All right, let's look at an example of this stuff. Okay, so again, this is all idealized motion. Okay, so there's parametrics. Let's get rid of those, give ourselves a fresh slate. So a cannon has its barrel at the origin and fire a cannonball at 45-degree angle with initial speed 145 meters per second. My question is, where will the cannonball be after 5 seconds, assuming it doesn't hit anything like a pirate ship or something, right? All right, so, well, the length of V naught is 145. Remember, I don't care about the direction even here. The direction affects the angle certainly, but the length here is what I care about. The length is 145. The angle is 45 degrees. Gravity is 9.8. And t is equal to 5, right? Okay? So I care about position when t is 5. So I plug into my equations. I got 145 cosine 45 degrees times 5. That whole big mess is the ith component. And then in the jth component, I've got what? 145 sine 45 degrees times 5 minus 1/2, 9.8, and t squared over here. That whole big mess is the jth component, right? So what is this here? 145 times 5 is apparently 725. Cosine 45 degrees is root 2 over 2. That looks good. And so that's the ith component. Over here, You got, what, 725 times root 2 over 2 minus, what does that give you? 122.5 J, all right? And so that is 512.7 I plus 390.2 J. So Cannonball is what, 512.7 meters downrange, all right, and 390.2 meters in the air, right? Okay. So that's all well and good, but what's important to us is knowing about, well, what are the maximums of these things? How high will a given projectile fly? How long will it stay in the air? How far can I fire it under ideal assumptions? So let's get rid of this. We'll talk about maximums here. All right. So max height, flight time, and range. All right. Okay. Well, max height first. So, well, think about this. So an object is traveling in the upward direction at some velocity, right? It's going to hit its max height when that vertical velocity is 0, right? Because what goes up must come down. So it must hit 0 somewhere in the flight time and then begin going in the opposite direction as it comes back down again, right? So the max height occurs when vertical velocity is equal to 0, right? Should really say the 0 vector here, but so i.e. when the derivative of the jth component is equal to component of r of t is what I should say, of r of t is 0, right? Okay, well, here is the jth component from parametric, so it's this big thing, sine, that should be an alpha, alpha t minus 1/2 gt squared, right? That is the vertical position component. Well, I care about velocity, so I care about dy dt, right? So let's see here. So this is just v naught sine alpha. Remember, alpha is a constant here, so this just becomes v naught sine alpha. And this becomes what, minus minus gt? Is that what I've got here? Yes, good. All right. So there's the derivative, right? Well, let's set that thing equal to 0. V naught sine, this should be, yeah, gt, that's right. Set this thing equal to 0 and solve for t. So we get what? Negative gt equals negative v naught sine alpha. So t is equal to v naught sine alpha over g, right? Well, that's a t value, so this is the time of the max height. Well, that's all well and good to know about that, but I care about the actual vertical distance of max height, not the time so much that it occurs at. So I got to plug this thing back into my original y equation to get a maximum vertical distance. So let's boot this stuff out of here. So kick this out. We have that t. So I'm going to plug this into my y component. V naught sine alpha times all kinds of junk here, sine alpha, over g minus 1/2 g, and then v naught sine alpha over g, the whole thing squared, all right? So what does this give us here? So let's get rid of this. So over here we've got what? We've got V naught sine alpha squared over G. This is a G squared and a G, so that cancels, so that leaves a G down below. We got a 2 down there hanging around, so we've got V, that should be a V naught. So we got V naught sine alpha squared over 2G, right? Because this G cancels with that G squared, right? And so make a common denominator, put a 2 over here, so we get 2 V naught sine alpha squared minus V naught sine alpha squared all over G. And am I getting the right thing out of this here? Yeah, I am. Good. So this should be a 2G down there. Yeah, that looks better. So 2 V naught sine alpha squared minus 1 V naught sine alpha squared. Well, that gives us a V naught sine alpha squared all over 2G, right? So this is the actual maximum height, right? And notice this thing depends on the angle alpha, which should make sense to us, right? If you're going to fire it at a lower angle versus a higher angle, different max height is going to occur. Okay, so there's your max height formula. We'll try it out shortly, but let's go through flight time and range too. So let's get rid of max height. What am I doing next here? Flight time, yeah, all right, flight time. So the projectile lands when r of t is equal to 0 again, right? In other words, the position vector is 0. It started off at 0, it ends at 0 and hit the ground again, right? So that means that the vertical position, this should be sine of alpha, is going to be 0, gt squared, right? Actually, I said the wrong thing up here. This is not true. This should be when the j component of r of t is equal to 0. Yeah, that's a lot better, yeah. So, yes, good. All right, so the j component, right, the vertical distance is 0 is when this thing lands, right? All right, so once again, we have this formula for y. This time, I want to set it equal to 0. Remember, last time I used y's derivative to set it equal to 0. This time I'm using the actual y to set it equal to 0, right? Okay? So we can factor a t out of this. Get v naught sine alpha minus 1/2 gt equals 0. Well, so one of these solutions is t equals 0. Well, that's launch time. That's the time it was launched. So obviously, it's at position 0 then. We're saying that it is. So what's the other time? The other time is when this big expression, 1/2 gt, is equal to 0, right? Okay. So what is this? So this is negative v naught sine alpha equals negative 1/2 gt. So we need to multiply by negative 2 over g. So this gives us 2 v naught sine alpha over g is equal to t, which is that what I have here? Yeah, good, it is. This is the landing time. Yeah, okay. So there's the landing time. All right. And now, well, the max range comes directly out of the landing time, because when landing time has occurred, then we want to see how far the range is, right? So this is the flight time. This is as far as it's going to go. When it's gone this far, however far downfield it is the max range. So let me say that. So max range occurs when we plug landing time into the ith component, yes, the ith component of r of t as such, right? So we want to know how far downrange it is. The max range occurs when we plug in landing time into the horizontal component of r of t. All right, let's do that then. So let me erase all of this. Keep landing time in mind. All right, so remember, the ith component is v0 cosine alpha t. So I want to plug in my landing time to that. So I'll use capital R for the max range, v0 cosine alpha. And remember, my landing time was 2 v0 sine alpha over g. I don't need that big of parentheses, do I? All right, that was the landing time. So I'm going to plug that into my horizontal component here. All right, and then what in the world does this give you? Gives you v0 squared over g times 2 cosine alpha sine alpha. All right, and then what do you use here? Trig Identity, yeah. So if you think back to your catalog of trig identities that you got, this is sine 2 alpha. This 2 cosine alpha sine alpha. It's the same as sine 2 alpha, right? So this is going to be your max range. Well, we can get even better than that. So I said that, you know, height depends certainly on firing distance. So does range, or firing angle. Sorry, not distance, firing angle. So does range. So in particular, the range is maximized for any initial velocity when we maximize sine 2 alpha. 2 alpha is maximized. So what I'm saying is, certainly, if you're going to fire a projectile at a larger initial speed, it's going to go further, regardless of your angle, right? Okay? The fact is, though, you give me any initial velocity, v0, I can maximize the distance that it goes horizontally by maximizing this part of the max range, right? Because this part is going to get adjusted. G is constant. It depends on the angle, right? Well, the maximum that sine can ever be is 1. So sine 2 alpha can at max be 1 also, right? And so let's see, what do we do here? Take the inverse sine of both sides, right? So inverse sine of 1 is 90 degrees, right? So 2 alpha equals 90 degrees, and alpha equals 45 degrees. So for the longest range, alpha should be 45 degrees. And intuitively, this agrees with what we think about motion in the first place, is that if you're going to fire something, this 45-degree angle to the horizontal is the ideal angle to fire it at, right? If you fire it at a very steep angle, it's going to go up in the air and then plop back down again. At a very flat angle, it's going to kind of pancake out and just kind of land too soon as well. So this is the ideal firing angle, and this proves it, actually. Now, again, this is under ideal conditions, but still. Okay, so let's do an example of this stuff now. Let's find all these things for a certain projectile. So where am I here? So let's find max height, flight time, and range of the Cannonball from the previous example. Right? So remember that we're using the same examples before, so we have the same numbers. Remember, our Cannonball was fired at initial speed 145 meters per second. Our alpha was 45 degrees. That's nice. And our G is 9.8. Okay, well, max height, we'll call it y sub max. Call it that before? No, I didn't, I guess. But here we'll call it y sub max. So that is v naught times sine of alpha squared all over 2 times 9.8, right? That should look, how about that? There you go. All right, so you plug the numbers into the formula, you get about 536 meters in the air is the max height, right? And whatever time to achieve it, we don't care about that really, but we can get it very easily with the formula. The flight time, how long is this thing in the air for? So flight time, so here t is equal to 2 times the length of v naught times cosine alpha over g, right? I'm sorry, sine alpha over g, excuse me, sine alpha over g. But it's the same thing for 45-degree angle, so it doesn't matter. So this is about, what, 20.9 seconds? Okay. And the max range, so the range is r equals length of v naught squared over g times sine of 2 alpha, which is sine of 90 degrees, which is 1. This is sine of 90 degrees here. And that is 2,145 meters away. So that's something like almost a mile and a half. That's not too shabby, really, right? And also, notice, too, that this is max range for any projectile fired at initial velocity 145 meters per second under ideal conditions. It doesn't matter what we're firing here. The point is that our angle is 45 degrees. That is the angle that will produce the max range. So all we can alter now is the initial velocity. So anything I fire at this initial velocity will travel at this range when fired at this angle under the ideal conditions. Okay? All right, so there's max height, flight time, and range. Let's look at position vector here a minute. So get rid of this. The position vector of this thing, well, remember, we had an equation for r of t that we derived earlier on in the lecture. So position vector at time t is r of t equals, so what do we have, 145 root 2 over 2t. Remember that was, what, length of v naught times cosine alpha t for I. And then for j, we had 145 root 2 over 2 t minus 4.9 t squared. That was j, right? Remember that's length of v naught sine alpha t minus 1/2 gt squared, right? Okay. So there's your position vector. All right. Well, if I go to parametric mode, and I use the TI-89 here, but probably any calculator that has this mode will do. You can graph this thing. So can graph x equals 145 root 2 over 2t, and y equals that rigmarole minus 4.9 t squared. So you can graph this, and, well, what do you expect to get? Well, let's see here. So let's do 225. Up here we'll do 550. And along the bottom we'll do 500, 1,000, 1,500, 2,000, right? Well, so your max height was what, 536, and your range was 2145. So something that looks probably even a little too far out there, but so what do you expect to get here? A parabola, right? You expect ideal projectile motion to travel in a parabolic arc. All right? So you get, let's see, so as intuited, ideal motion is parabolic. Okay? So the graph tells us that, all right? Okay, now notice, remember, t is nowhere on here. So just x and y. T is the implicitly defined variable in the background. But this is position x and y at any given time t. Okay? We can do better than this, though. I mean, the graph certainly confirms our suspicions, but let's look at the equations again and see why this is actually true. All right? So let me get rid of all of this in the middle. I'll leave our parabola over there. So remember, our equations parametrically are x is your length of v naught cosine alpha t, and your y, you know by now, is your v naught sine alpha t minus 1/2 gt squared, right? Okay, so let's solve the first equation for t and then plug it into the second equation, and let's see what happens there. So the first equation, what do we get? We get x over v naught cosine alpha. That's t if we solve the first equation for t. Right? Okay. And if we plug into the second equation for t, let's see what happens here. So we get v naught sine alpha. Plug in this junk, so we got x over v naught cos, that should be there, cosine alpha, like that, minus 1/2 g, and then x over v naught cosine alpha squared. All right, so that's straight plugging in. Okay. Now let's do some simplification here. So do I do more than one step? Yeah. Okay. We can do that. So this is v naught sine alpha over v naught cosine alpha. That's the coefficient of just x, right? That thing there is x's coefficient, okay? And over here, what have we got? We've got g over 2 v naught cosine, or v naught, I should say v naught squared, 2 v naught squared cosine squared alpha. Catch everything there? And that thing there is the coefficient of x squared, right? Okay, is that what I've got? Looks good, yeah, sure. So now let's rewrite this up here. So we get y equals negative g over 2 v naught squared cosine squared alpha. And that's the x squared term. The v naughts over here will cancel. Sine over cosine is tangent. So we get plus tangent alpha x. And hey, lo and behold, that is an equation that is quadratic. So this is quadratic, right? And therefore it graphs a parabola for parabola, right? And notice here that the only problem that could possibly come up is that we can't very well have funky angles, things like cosine equaling 0, but that's dumb anyway because cosine is 0 when you fire things at pi over 2 angles, things like that, and well, that's going to be kind of a silly thing going on there. So you know, as long as your angle is not right up in the air or something else or straight down, you'll be fine. Okay, so this confirms our suspicion that in fact ideal motion should result in parabolas. Okay, all right. One more thing to do here. So we've assumed all along that we've started off firing our projectile at the origin. Well, the nice thing is that it doesn't really make a difference if we move it somewhere else, either it just adds on a little bit of stuff to our position vector. So now let's examine how do things change if we move our initial position. So if we change initial position from 0, 0 to, say, x naught, y naught, well, absolutely nothing surprising happens. Our position vector changes. We just add on the appropriate components, and the motion stays the same because the motion doesn't care where we start from, right? Doesn't make a difference whether we fire the cannonball from right in front of me or 10 feet down the road. The motion's going to be the same, right? So there shouldn't be a surprise at all. And then y naught plus, where's all this junk? Yeah, so v naught sine alpha t minus 1/2 gt squared is the jth component of things, right? Okay, and so this is going to be the new position vector. So this is the position vector. I guess I'll say new position vector. Okay, all right, let's do an example here. So we can make this topical. So a baseball is hit 3 feet above ground level at an angle of 25 degrees above the horizontal. And let's say this guy really got a hold of this one, and so its initial speed is 88 miles per hour, right? So the question is, on everybody's mind, will the ball clear a 10-foot wall that is 380 feet dead ahead of the batter, right? So if you're watching a baseball game and you see this hit happen, you can calculate right away, is it a home run or not, before you even have to watch it on TV. Okay, assuming this is obviously traveling, ideally, which is not in real life. But, so what do we want? First thing we want is miles per hour in feet per second. All right, and also I want to note here, noting the conversion factor that 1 meter is 3.3 feet. That will help us get gravity in terms of feet per second. So we'll do an old chemistry trick here. We'll just do a conversion. 88 miles over 1 hour is 5,280 feet in 1 mile. And 1 hour over 3,600 seconds. And so what do you get? The initial velocity is 129.1 feet per second is initial velocity. Okay. All right. So let me, I'll keep going on down here. I got some room. So V naught is 129. Alpha is 25 degrees. G is 32 feet per second, right? It's 9.8 times 3.3 is 32. Now, the position initially, well, x is still 0, but now it's 3 feet above the ground, so now our y naught is equal to 3, okay? So let me, let's see. So let me show that for a second here, and then erase some of this top stuff. All right, and in fact, we can just go ahead and erase this stuff and give ourselves room to work. So we have our information. We can now, what we need to do. So our question is, well, when the ball has traveled 380 feet in the horizontal direction, what time is it? And then at that time, what is the vertical distance? That's how we're going to approach this. So we want to set the ith component equal to 380 and solve for t. In other words, we want to figure out how much time has elapsed when the ball gets to the wall, and then ask ourselves how high in the air is the ball then? Is it taller than the wall, or is it not taller than the wall? Okay, so we have 380 equals 129.1 times the cosine of 25 degrees times t. Divide by that garbage, and you get t is equal to 3.25 seconds when it finally gets to that point. So taking it that long to get to the wall. Now the question is, well, what is the ball's height at time 3.25 seconds? All right. Okay. So now what is the y component at that time? Well, remember, y has that extra y naught piece in it this time, so it's 3 plus all the rest of this junk. 129.1 times sine 25 degrees times 3.25 minus 1/2. Remember, we converted gravity. Otherwise, you're going to get a funky answer if you don't convert. Times 3.25 squared. And let's see. You do all that out, you get 3 plus 177.32 minus 169, and you get 11.32 feet in the air. So this thing just barely clears it, so just barely clears the wall. And to put it in perspective, had the hitter gone down and hit a very low pitch, only a foot above the ground, this thing would not have cleared it. It would have fallen half a foot short. Okay, so that concludes the section on ideal projectile motion.